Okay. Try to sharing something. So, is everyone can hear me? Can everyone hear my voice? Okay, thank you. So it's like a test sharing. I'll test something. Can everybody see my screen sharing right now? Can everybody see my slide are sharing right now? Thank you. What's happening?
Hi, Waylon, can you hear me?
Okay. I can hear you.
I say okay. I should, now, but the first speaker is okay, but it is a time for the second speaker. So, uh, Koya-san, could you share the screen and speak something? Can you hear me, Koya-san?
Okay, okay.
I see. Okay, I can hear your voice.
Thank you.
Okay, so it's so for your time. But it is not your time. Sorry. But so the second speaker is not here yet.
Oh, yes, yes.
Uh, okay. Do you some instruction, Reza? Do you have some instruction in such a case? Hmm. Um, can you hear my voice?
Yes, okay.
Yes, I know you can hear my voice. So how about the technical assistant? Reza, can you hear my voice? Okay, yes, but I cannot hear your voice. So I don't know who is participating. So is there Takahashi-san? No. Is there Elise-san? Okay, I see. Thank you, Reza. So actually, I don't know who is participating. So now my name is not appear in the yeah in the panel. So there is another fellow, but I don't know who is.
松古さん,
はい。
can you hear me?
Yes.
So, from the conference room,
Yeah,
I can talk to you.
I see. I don't know what is the status. Okay, so anyway, let us prepare for the next speaker. Please share your screen, Koya-san.
Yes, okay. Sorry, wait a minute.
So considering the case, so the first and second speaker appears. So we should start the Koya-san's session, Koya-san's talk.
Can you see my slide?
Yes, I can see your slide.
Okay. Okay. Now, can I start my talk?
Yes, please.
Okay. Thank you for your. Thank you for. Sorry, wait a minute.
Okay.
Okay. I'm sorry. My talk is assessing the performance of mixed precision ILU0 preconditioned multiple precision real and complex real substance method. I'm Tomonori Koya at Otemon Gakuen University in Japan. This is the outline of our talk. First, we show the goal of our study. Next, we explain our implemented mixed and multiple precision floating point arithmetic and mixed precision SPMB arithmetic. And third, we explain the implementation of ILU0 preconditioning and explain the performance evaluation of our implemented preconditioning. Finally, we conclude our talk and we show future work. This is the goal of our study to solve ill-conditioned problems that are sensitive to rounding errors using multiple precision floating point arithmetic. We developed a BLC MATMUL. BLC MATMUL have two types of multiple precision arithmetic. One is multi-component way, and another is arbitrary precision way. To reduce memory usage, support for sparse matrices was needed. So we have just implemented real and complex SPMB and preconditioning functionality. But there are many issues remain to improve the performance of preconditioning functionality, ILU zero decomposition. Now the figure shows the current status of our BLC MATMUL library. The current published version is 0.21, and that is real computation. But we are preparing the next release version 2.22, including complex linear computation, including SPMB computation. There are some related works to our talk. Especially we should have compare with Riz and Hishinuma SPMB computation study, but now there are some enough time to evaluate this study. So we show the evaluation of our implemented multiple precision SPMB. Multiple precision SPMB is based on previously implemented in 2012 with MPFR library. And our implemented SPMB arithmetic can use a mixed precision floating point arithmetic like this. So we can use double precision SPMB to get multi-precision result and by using our BNC MATMU library. Our SPMB is supporting CRS type and SPMB and also including SP transpose matrix vector multiplication like this. And our implemented one SPMB can be parallelized and optimized by using MVX2. But SP transpose matrix vector multiplication is not so fast because including the process a critical section in the final one. So SP transpose MV is slower than SPMV computation. And in this talk, we will show the benchmark test of curious subspace methods by CG, CGS, by CG stub, and GP by CG algorithms. This is the algorithm of by CG algorithm, including preconditioning preconditioning parts in line 5, 6, 19, and 20. Our implemented curious subspace method with preconditioning process support both real and complex linear equations. And this is the algorithms of our implemented ILU0 factorization and forward and backward substitution via ILU0 factorization. ILU0 is no fill-in in the process of the factorization process, and of course, in a forward and backward substitution, there is no fill-in. But current, as described, as explained before, they are not optimized for AVX2 and not parallelizing. So our current implementation of preconditioning process is not so high performance. Now we show the result of our benchmark test. Computational environment is AVX AMD EPIC multi-core CPUs, and we use Intel compiler to compile our BNC MATMU and other related routines. And as linear equations, real and complex equations, we use the true vectors x like this, and we can all benchmark tests is using these two real and complex linear equations to evaluate curious subspace methods, including preconditioning process. In our curious subspace method, there are some computation, SPMB, SP transpose MP in the product, and AXP computation like this. And stopping rule is residual vector. The norm of residual vector when residual vector is smaller than this value, we stop the process of Coulomb subspace algorithms. Or when the number of iteration is reaching this 3 times dimensional number, Coulomb subspace method is stopping. And we use the two matrices are used in our benchmark test. One is MCFE matrix. That is real sparse matrix, and as a complex sparse matrix, we use DWZ 961V matrix. The reason why we pick up two matrices, this matrix, the linear equations, including these matrices, cannot converge by without preconditioning a process. So the result, this is a table showing is showing the result benchmark test by using solving linear equation with MCFE matrices. In tables, the result of double precision, triple precision, and quadruple precision. As the table is showing, without ideal preconditioning, all methods cannot converge without ideal zero preconditioning. And also we can find that we can understand that by using double precision, mixed precision, and computation, in this case, the convergent is not so changed by using double precision, ideal zero decomposition, and mixed precision, SPMB arithmetic. The table shows the result of solving complex linear equation, including DWG 961B matrices. As the table is showing, compared with the real linear computation case, solving complex linear solving complex linear equations takes more time. Of course, that is a very normal one, and and we can understand that the ideal zero preconditioning is significantly higher by using double precision computation. And the table shows the cases when we use MPFR, arbitrary precision arithmetic. In this case, we select 256-bit computation. So in this case, we can find that some cases in complex linear equations, some cases show the show the non-unconvergent one. Double precision preconditioning is not can be giving bad effect to converge Courier subspace method. But when the mixed precision, double precision, SPMB, and LU decomposition is successful, the performance is very the performance is better than without mixed precision, purely multi-precision computation. So this is a summary of performance ILU decomposition. Decomposition. In this, as the table showing, ILU preconditioning increases total time by factors like this, and mixed precision using double precision, mixed precision, arithmetic reduce time but 4%, 4 to 5% compared to standard purely multiple precision ILU decomposition. For 256 bit, when the convergence is successful, mixed precision, double precision, arithmetic yield up to 47 to 48% reduction in ILU zero cost. In complex linear equations, the trend is more clearer than using real linear equations. So we can conclude that the computational cost of ILU zero decomposition increases with higher arithmetic precision, and in any types of floating point arithmetic. Of course, in MPFR arbitrary precision arithmetic, ILU zero decomposition is effective, and when the convergence is successful by using mixed precision, double precision, ILU decomposition, and SPMB computation, the performance is better than purely multiple precision computation. Of course, for solving complex linear equations, the benefit of mixed precision is more profounded when using multi-component types and MPC any arbitrary precision arithmetic. So as a future work, we want to improve the performance of BNC matmu. Of course, the ILU decomposition and forward and backward substitution should be improved by using CMIT optimization and OpenMP parallelization. We expand the functionality of our BNC matmu library. Another type of implementation can be run on new and another type of computational environment, including ARM Neon, Watson, and SSE that have 128 SIMD instructions. That's all. Thank you for your attention. Thank you.
Thank you very much, Koya-san. So there is just 1 or 2 minutes for question and comment. Do you have some question or comment? So if you have, please unmute and speak. Just ask. So I have one question about the performance. So you applied AVX2. So what is the performance in the measure of floating point X flops compared
Flops?
to the peak performance? Yeah.
Sorry, I have no information of exactly accurate Fox value, AVX by using AVX2 to implement SPMV arithmetic. There are many cases can be improved. I can only I can say some improvement can be found in our benchmark test. Sorry.
I see. So you mean so at least by employing the AVX2, so the SIMD acceleration is indeed obtained.
Yes.
I see. Thank you. So the time is running. So thank you very much, Tomonori, again. Then maybe we should rearrange the talk. So now I can see the first speaker. So Takahashi-san, can you hear my voice?
Yes, I'm Shigeru Takahashi.
Okay, I see. Thank you very much. So then maybe we should rearrange the order. I would like to ask Takahashi-san to the next talk, and then so we should delay. We should the shift the other two talks 20 minutes later. Is there Elise, the second speaker? Okay, no, not. So, okay, then so we should start the first talk. Please start, Takashi-san.
Okay, thank you, Chairman. Can you see my slide?
Yes.
Okay. Then, good morning. I'm Shigeru Takahashi from University of Tokyo. Today, I'll talk about NAFCAL, a simulation tool for analyzing acid flux densities observed with ALMA. Of the ALMA. This work was collaborated with Kyoto Sanyo University, Ashikaga University, and others. First, let me briefly introduce ALMA, the Atacama Large Millimeter Array. ALMA is one of the most powerful radio interferometers in the world. It is located in the Atacama Desert in northern Chile at an altitude of 5,000 meters. The array consists of 66 high-precision antennas. Among them, 50 antennas have 12-meter dishes and 16 7-meter antennas. These antennas can be spread out over a maximum distance about 16 kilometers. ALMA operates across a wide range of wavelengths from 0.3 to 9.6 millimeters, covering both sub-millimeter and millimeter regimes. Thanks to this large baseline and short wavelengths, ALMA can achieve an angular resolution better than 0.01 arcseconds. Such high spatial resolution allowed us to study detailed temperature structures on the surface of solar system bodies. I will talk after thermal emission. Asteroids emit thermal radiation in the submillimeter and millimeter wavelengths. However, before the construction of ALMA, we faced two major limitations. First, it was difficult to spatially resolve the surface of an asteroid. The largest asteroid in the main belt is 1 Ceres, and its diameter is about 960 kilometers, but we couldn't resolve from ground-based telescopes. Second, small or faint asteroids could not be detected due to insufficient sensitivity. But ALMA has greatly changed this situation. ALMA attained high spatial resolution, and for large asteroids like 1 Ceres can now be resolved and investigated precisely on the surface. And thanks to ALMA's high sensitivity, we can observe smaller and fainter bodies in the solar system. ALMA opened a new window to the asteroid studies. And then now, as the amount of asteroid data increases, it has become necessary to develop a tool for ALMA data analysis. For that purpose, we developed AFCO. It stands for our asteroid flux. It stands for Asteroid Flux Density Calculator for ALMA. AFCO is a Python-based simulation tool. It computes the brightness, temperature, and the flux density of an asteroid using a thermophysical model. Although some similar tools like AFCO have been developed in the past, this is the first tool to incorporate surface roughness into the analysis. The main goals of AFCO are as follows. First, it predicts flux densities at millimeter and submillimeter wavelengths. Second, it helps interpret ALMA observations using physics-based modeling. Third, it supports observational planning and data analysis. Let me now explain the thermal model used in AFCO. At the surface, we consider three components in the energy balance. Solar absorption is shown in yellow. This represents the incoming sunlight absorbed by the surface. And thermal radiation is shown is green. And this is a heat emitted back to space. And it follows the Stefan Boltzmann law, which states that radiated energy is proportional to the force power of the temperature. However, because the surface of most asteroids are covered with regolith, which is a layer of rough material, the emission is not perfectly isotropic. To model this effect, Roglini et al. Introduced a roughness parameter Z, which accounts for surface microstructures. The effect emission is then given by the denoted X equations. This collection is important to simulate the realistic infrared and millimeter wave emission from regolith surfaces. Conduction into the surface is shown in brown. This represents heat flowing downward into the interior, which we model using the one-dimensional heat conduction equation. In addition, we include surface thermal radiation, or STR. This is important because at millimeter wavelengths, radiation can come from below the surface. We calculate this by integrating the temperature distribution with depth. This is essential for interpreting the brightness temperature observed by ALMA. And then I'll explain how the numerical calculations were done in this study. We start by using a shape model from the DAMIT database. These models are derived from Markov inversion techniques based on photometric observations from ground-based telescopes. This database is offered by Charles University in the Czech Republic. Using these shapes, we can compute the incident solar flux and emission directions for each surface facet. Next, we obtain the ephemeris data from the JPL horizon system. This gives us the asteroid's position, orientation, and rotation at the time of observation. For the thermal simulation, we solve the one-dimensional heat conduction equation on each polygon facet using an explicit infinite difference scheme. Each facet is treated independently, so we use Python's multiprocessing module to perform calculations in parallel. The entire simulation was run on MDX, a high-performance computing service operated by the University of Tokyo. Specifically, we use the CPU nodes equipped with the Intel Xeon Platinum 8368 processors, which allowed us to handle hundreds of facets simultaneously. This computational setup enabled us to simulate realistic temperature distributions with reasonable runtime, even for detailed shape models. Now I will explain the calculation flow of NAFCO. We begin with the data input step. First, we load the asteroid shape model and ephemeris. Then we set the physical parameters such as thermal inertia, emissivity, and the spin axis. The spin axis is aligned to match the correct celestial position, and then once the geometry's parameters are ready, we perform the initial thermophysical model TPM step. Here, we run the thermal simulation until the surface temperature profile reaches equilibrium. After the equilibrium, we proceed to the TPM simulation. We solve the 1D heat conduction, and this step is executed in parallel using Python's multiprocessing module, which speeds up the calculation significantly. Then we integrate the emission from beneath the surface, and finally we carry out the intensity calculation, then make a map of the flux and the temperatures. In this study, we applied FGO to two asteroids, 1 Ceres and 3200 Phaeton. First, Ceres is a dwarf planet located in the main belt, and it follows a nearly circular orbit at about 2.77 astronomical units, and its orbital period is roughly 4.6 years. Because of its size and stability, Ceres is often used as a flux calculator of Raman observations. On the other hand, 32,000 Phaeton is a near-Earth asteroid of the Apollo type. It has a highly It's a highly eccentric orbit with the pay-helm distance is about 0.14 AU, which brings it even closer to the Sun than Mercury. Its aphelion extends to about 2.4 AU, and its orbital period is about 1.43 years. Phaeton is best known as the parent body of the Gemini meteor shower, and it also targets the JAXA's Destiny Plus mission scheduled for launch in the near future. These two targets represent very different thermal environments, and they provide a good test cases for evaluating FGO's capabilities. Let's now present the result of 1 Ceres. Ceres is observed using armor band 6 at 265 GHz on October 19, 2017. According to the observational data, the brightness temperature was about 179 Kelvin, and the flux density is about 1.60 Jansky. And calculated results of the FGO is the brightness temperature is about 173 Kelvin, and the flux density is 1.62 Jansky. And due to the rotation, Perhaps the brightness temperature varied slightly between the 172 Kelvin to 174 Kelvin. And also, we need the comparison with the mid-infrared data. In mid-infrared case, we calculated its brightness temperature is about 200 Kelvin and higher than the ALMA's observation. 27 Kelvin higher compared to with the ALMA's data, and the Fluxy is 50% is higher. And this difference emphasizes that the importance of including surface thermal radiation when modeling emission in the millimeter wavelength range. Overall, our model reproduced the observation data well. Now let me show the results for 3 to delta pattern. We simulated the brightness temperature and the flux density at 2 orbital positions, at perihelion and aphelion. At aphelion on December 23rd, 2027, the brightness temperature reached 280 Kelvin, and flux density will be 7.4 millijanskis. And on the other hand, at aphelion 2028, October 27th, brightness temperature will be 199 Kelvin, and the flux density will be 169 microjansky. And these results difference demonstrates that the 81 Kelvin lower at aphelion and flux density will be 44 times lower than the at aphelion. These results demonstrate that how strongly thermal emission depends on solar distance, and it will be helpful for planning future observations such as Destiny Plus mission. And we also evaluate the explained parallel performance of evaluation to the AFCO. AFCO uses Python's multiprocessing module to parallelize numerical calculations. We tested this using the case of one series and modeled with 800 facets. This figure shows the computation time as a function of the number of CPU's cores. This figure shows the x-axis denotes the number of cores used in the multiprocessing module, and the y-axis shows the total computation time in hours. As increasing the number of cores, the time decreases almost linearly, which demonstrates that alpha is highly polarizable. With a single core, the total computation time is about 4.98 hours. When using 120 cores, the speed up reaches maximum as core number 55. We applied the Amdahl's law to estimate the polarizable fraction. From the measured maximum speed up, we obtained 98.2% of the computation can be polarized. This indicates that alpha achieves very high polar efficiency. And finally, I'd like to introduce some future directions for the AFCO. First, regarding algorithmic improvements, we are exploring the use of neural networks to accelerate the heat conduction calculation. For example, Zhao et al. 2024 demonstrates that the deep operator networks can potentially achieve a speed up of 5 orders of magnitude. In addition, we are considering GPU acceleration using a frame network such as JAX or CUDA to further reduce computational time and support large-scale simulations. Second, for scientific applications, we plan to apply AFCO to a wide range of ALMA asteroid observations. This includes not only main-belt asteroids, but also near-Earth objects and possibly Centaur or TNRs. We aim to support the integration of archival ALMA data as well as the future observation campaigns. Third, we are planning several model enhancements. For instance, we will implement layered surface structures, including dust mantles and volatile-rich subsurfaces. And we also plan to extend the model to binary asteroid systems. taking into account the mutual shadowing and self-heating effects. And these improvements will make AFCO to more powerful tool for small body thermophysics and observation support. In the summary, here, developing AFCO and solve one heat. AFCO solved 1D heat conduction power process and implement efficient parallel computation using multiprocessing and validated ALMA observation 1 series with high accuracy, supports mission operation and observing planning, and features applies GP acceleration, neural operator integration, and layers models, etc. Thank you very much. That's all.
Thank you very much, Takahashi-san. So we have about 2 minutes for questions and comment. So if you have some comments or questions, please unmute and just tell him, ask him. So I have 2 questions, but let me ask one. So what is the typical time scale of the equilibration? Because so for Ceres, so it is almost a circle. So but for the Phaeton, so it's very
Complicated.
how to say? Yeah.
Yes. It depends on the number of facets. Typically, series case is one CPU would be a 4.9, almost 5 hours. But Python's case is facets will be 4 times larger, about 3,000. So that for a single core case, equilibrium time would be 4 times. So 4 times is 4 times. So that for single core, it will be 1 day, almost 1 day.
I see. So you answered about the computational time. What is a physical time scale?
Physical time scale.
Yes.
I haven't checked very well, so.
I mean, so perhaps it is also possible by your software to understand how it is cooled and how it is so warmed in real real environment.
Yes. So, but in this case, it takes about most cases 1 or 2 days in the multi processing in the one location. Yeah.
I see. So it's so enough time to be equilibrium.
Yeah. In this case, so I want to so improve the hours. I should do it.
Okay. Thank you very much. Is there any comment or questions? Okay, so time is almost running. So thank you very much, Takahashi-san, again.
Thank you very much.
Okay, the next speaker is Wei-Lun Chen. Could you share and start the talk?
Okay, you hear me? Can everybody hear my voice? Azul-san?
Yes.
Okay. Please wait a moment. Can everybody see my screen sharing right now?
Oh, okay. Yes, please. Well, but this is your. Okay, now you are showing your kind of manuscript. Please switch to please switch to the slide.
Oh, it's not showing my slide right now?
Not a slide.
I see.
No, you are sharing.
Else. Okay, see. It's now correct?
Now it's correct.
Okay.
Please start.
Thank you. So sorry for delay. So I'm Wei-Lun Chen from Sokendai KK. So I'm going to introduce this title, Accelerating Interactive Linear Software using Modified Domain Fermion Matrix, and that is QC simulation. So this will collaborate with Kanamo Isaku and India Matsufuru-san, and also Hamad Neef-san. So here's my outline. So first, I'm going to introduce what is quick review what is that is QCD, and going to introduce the domain of fermion, and we are introduce the main topic, which is the alpha improvement to the domain of fermion, and we are going to measure the condition number and the iteration, and we'll go to our summary. So QCD is a quantum field theory describing the particles such like quark and gluons, and this theory needs to be calculated numerically due to its nature. So lattice QCD is one of the methods to calculate QCD numerically. So here we have on the right hand side we have a 4-dimensional Euclidean hypercube, and each side in the hypercube there's a quark, and the quarks are connected by the linked gluons. So current symmetry, which is a fundamental symmetry of QCD, now is multiplied by this lattice spacing. So the property of the hadrons now are obtained by inverting the fermion matrix D. We're talking about what is this matrix later, and inverting this matrix is the main bottleneck of the lattice QCD simulation. In order to obtain the precise physics result, we need a very large volume of the hypercube, and also we need a very small quark mass input. So these two conditions introduce a very huge condition number to our fermion matrix. So lattice QCD have a lot of different actions, but they have to be coincident to the QCD in the continuum limit after we take A to the 0. So I will review some of the common lattice QCD fermion. So first one we're going to introduce is the Wilson fermion, and in this for Wilson fermion, the chiral symmetry is totally broken, and its numerical code is not that high. And our target, which is the domain fermion, have a almost exact chiral symmetry, and they have a relatively high numerical codes. And we also have overlap fermion. You have a vast chiral symmetry, I'm intended, but the numerical code is extremely high. So the feature of the domain fermion, which is our target, is have a very good chiral symmetry with controllable numerical codes. And this theory itself introduced an extra fifth dimension to the theory, and each fifth dimension coordinate there's a Wilson matrix deep inside. So let me introduce what is the Wilson fermion. So here we have equation. So x and y here are the lattice coordinate on the hypercube. So the first term here, delta xy means the local interaction, which is the coordinate acting on the same coordinate, and the second term here is the connection between this coordinate and its neighborhood. So each neighborhood are connected with their neighborhood by a gauge link, which is the gluon we talked about before. So you can imagine things is living in the 4 dimension. This is like 9-point standstill computation, and each connection have a connected by gluon, which is a 3x3 compressed matrix, and also they have another degree of freedom. We call it spinner. So what is domain of fermion? As we before mentioned, this is like we introduce an extra dimension. So if you look at the theory in the extra dimension, we can build a 5th dimensional matrix side. So the matrix is building on the right hand side here. So in each 5th dimensional coordinate, we have D plus B, D minus here, and its structure is like the 4-dimensional Wilson fermion matrix multiplied some constant, and then loop over the 5th dimension. So this is like and we it is something we have to notice, like there's no gauge link connected on between the 5th dimensional side. So now the chiral symmetry breaking on the lattice is multiplied by the B and C, and also the Wilson fermion coequivalency from the Wilson matrix, and also the 5th dimensional length NS. And there's an interesting property of the this 5th dimensional matrix, and its eigenvalue is not guaranteed to have any negative real part. So if we want to solve it, we need to solve by the D dagger D instead. And in between, only the edge of for the solution, only when coordinate equal to the edge, the solution is relevant to the 4D physics. So it means we only need coordinate in the edge of 5th dimension. So in order to accelerate our domain wall solver, we introduce an additional parameter alpha from proposed by Hamad Nefsan. And we see now the matrix is modified into this form. So when alpha equal to 1, we get the dW will return back to the original domain of fermion, because there's another property which P minus plus P plus will equal to 1. So it will return back to the original matrix. And for alpha not equal to 1, the condition number will change. So we going to investigate what is the condition number changing under a different alpha. So the most important thing of the series, like all of the solution itself is changed, but the only relevant choice, which is the solution on the edge, is unchanged. Here we write down the equation here, so the s equal to 1 still unchanged. So we can guarantee we obtain the same physics after we introduce this new parameter. And the number of the floating number operation is almost unchanged. So this is still like a memory bound computation. So let me talk about our numerical setup. So first thing we set up is the even or precondition. So we separated the side by its even or odd. So we look at right hand side, there's a figure over here. So for first black dot here is like origin, so it's 2 dimensions, so it's like a 0, 0. So 0 plus 0 is 0. So this is the even side. For the right hand side here, is x equal to 1 with y still 0. So this is 1 plus 0 is 1. So this is odd side. So by separating even and odd side, because we know the gauge link only connected the point and its neighboring point. So it means the gauge link can never connected the even and even side or odd and odd side. So by changing the linear equation from the first line to the second line, we expected the condition number will drop due to the physics nature. So we will test our alpha improvement under this kind of preconditioning method. So now we are going to measure two quantity. The first is the iteration number of the CGI to converge. And the second thing we measure is the condition number of the d dagger d, which we measure the ratio between the maximum eigenvalue and the minimum eigenvalue. So we use the implicit restart long cost to test the eigenvalue. So we use the Pegasus system in the Tsukuba University as a tool to computation. And for physical domain setup, we have several kind of different settings. So first, we have prepared two kind of lattice spacing. The first one is 0.1 fermion. So it is characterized by the beta equal to 6.0, and with the total lattice value equal to 16 to the 4 and 32 to the 4. And for the bigger lattice spacing, we have a beta equal to 5.7 with the only single lattice value. Okay, so we have another setting which is a domain wall high. We prepare two kind of domain wall high. So first one is 1.0, which is with link smearing. Another one is 1.8 without link smearing. So link smearing is a method which smoothing the gauge link to reduce the finite lattice spacing effect. So I pick up these two values because they are common selection of the lattice simulation. And also coefficient parameters, we have B equal to 1.5 and C equal to 0.5, which is the common Möbius setting. And there's also another one with B and C are both equal to 1. We call it Borchardt setting. And we also test two kinds of fifth dimension lengths, which is 8 and 16, to test what happened if we change the fifth dimension side. And for each different setting, we use three kinds of quench configurations. And we also test the different kind of value of a clock masses, from very, very low masses like 0.001 to the relatively heavier 0.01. So I'm going to talk about the results. So this is the number of the software to converge, the iteration number. So here you look at this diagram, we look at the alpha to the 1.0, which is the original domain fermion. And we can observe that after we lower the alpha, all the iteration becomes smaller than the alpha equal to 1.0. So we can observe that alpha indeed improve the rate of converge to the linear software. And the best best value of alpha is around 0.5, which improves 37% comparing to alpha to 0, and for all the methods. So next slide we're going to show is this is the previous diagram on the left-hand side. And the right-hand side here, what we measured is the condition number normalized by the condition number measured in when alpha equal to 1. So this is in order to cancel the fluctuation. So the condition number, the tendency of condition number changing by alpha is quite consistent to the iteration number change against alpha. So we can observe the improvements are really due to the reduction of the condition number. Sorry. So now we're going to change the lattice volume from 16 to the cube to the 32 to 4. Not cube, sorry. So 16 to the fourth, and from 16 to the fourth to 32 to the fourth. So now we observe for the tendency to the alpha is still similar. We can observe the alpha is still improving the performance in larger lattice volume, but the quantum dependence looks a little bit different from the previous result, because the previous result are suffer from finite volume effect. So I think here is more nature behavior for lattice simulation, and the best alpha now is lying between 0.5 to 0.6. Since we don't have a time, let me just put a summary table of all results. So we found that optimal alpha lies between 0.6 to 0.4, and this reduces the CG iteration by 20 to 40%. And we observe oscillation happen for all the tested cases here. So for all this kind of setting, we observe the oscillation. Okay, so let me go to my summary. So here we want to say that introducing the alpha really accelerated the convergence to the domain fermion by 20 to 40%. So the acceleration is best around alpha near 0.5, and the condition number is consistent with the changing of the condition number, changing of the iteration number. So are we going to implement this alpha to all our code, and we want to propagate this code CERN, and we want to investigate what is the changing of another feature of the domain fermion, such as residual mass or something. And the most important thing is, like, we want to understand what is the background mechanism of this alpha. So my talk is ending here. Thank you, everybody.
Thank you very much, William. So now session is open to the questions and comment. So if you have questions or comments, so please unmute and just ask him. Any questions? Comment? Okay, if not, so the time is already a bit behind. So thank you very much, William. Okay, the last speaker is so from the in presence. So please share the screen.
Just a second.
Yes.
Can you share your screen? Just a moment. This is right?
Yes.
Can you see the screen?
Yes, but not the slide, not yet.
Yes, you can start.
We can see your slide, your
No.
screen. Yep.
It's not shared.
Not sure.
Not shared yet.
Okay. Window.
No.
This one.
Room.
Oh, this. Okay. Is it okay now?
Yes. Please
You can
start.
start.
Yes. Now, university network is done, and in the conference room, we cannot use network. And first, I have used Edrom network, but now I can't use. So now this presentation maybe out network out of network this university. First of all I would like to thank organizers to present my recent works. I'm Aoyama from KEK Computing Research Center. First, I would like to explain Gaussian expansion method. This is a basic method for this presentation. First, I would like to explain two-body system for simplicity. In the GEM, in GEM, we use Gaussian expansion for basis wave function or basis function. And this basis function is expressed by Gaussian. And this P is important in this talk. This is Gaussian with parameter. And next, I would like to explain Jacobi coordinate for helium polymer. In this presentation, I apply the present method to three-body system. It is a typical one, helium 4 polymer, helium 4 atom three-body system. Jacobi coordinate is expressed like this. Between helium 4, first coordinate is R1 and second coordinate is R2. And quantum number is L1 and L2. And basis function is B1 and B2. These are with parameter. And usually for solving helium for polymer in GEM, we use 500 basis function to 1000 basis function. This is a typical number of basis functions. And in the present calculation, we based on these precise calculation using these basis function. 400 basis function for L1 equals 0, L2 equals 0, and L equals 0. And 200 to 5 basis function for L1 equals 2 and L2 equals L equals 0. And the total number is 625 basis function. And precise energy by using this basis function, energy is minus 0.125 millikelvin. This is a reference calculation or a benchmark benchmark calculation. And now we are planning to solve about 10-body system because around 10-body system, at least in nuclear physics, we can connect other method like non-Gaussian model. So we can now want to solve 10-body system, but usually in GEM, front line is 5-body system, and even 4-body system, solving 4-body system is very difficult problem. And so we apply several methods. For example, MPI plus OpenMP, and quantum computing, machine learning, GPU computing, and development of numerical algorithms. And main bottlenecks for extending to two-body system is the number of basis function, which consumes computer memory, and the number of core in the supercomputer. So our problem is how to reduce the number of the basis function. Here I would like to explain the basic recipe for stochastic variational method. In the ICE step, first, randomly choose an ICE basis function. And second, the Hamiltonian matrix is calculated using the basis function selected up to I minus 1 and ICE basis function, and is diagonalized. We obtain the energy. If the difference in energy after diagonalization with the energy for the ICE is larger than the difference energy, it is adapted as a basis function. If not, we don't adapt them. This is a basic recipe for stochastic variational method. Here I would like to show SVM calculation of helium for Tollimer. Horizontal axis is the number of trials to diagonalize the Hamiltonian, and vertical is the energy. And if we perform the stochastic variational method, energy becomes to the precise energy minus 0.125 Kelvin. This is obtained the conventional GEM calculation with 600 to 5 MeV. And you can see very quick convergence around this region. About 25 trial and employed basis function is about 100. So stochastic variational method works very well. But this method has been already discussed by many groups. And I want to show details because if we change the
excuse me, we will have 15 minutes of delay.
Yeah.
So everything is shift 15 minutes because of the delay. Thank you.
Go on, please.
And there I want to show five calculations. Essentially base is the same, but combination is different. And all 5 calculations shows the quick convergence around 200 and 200 trials, and most smallest number of the smallest number of basis function is 19 for try 2. This is a basis function employed, not try number. Try number is 410. And all 5 calculations shows the similar, same energy. These are precise energy. And now one stochastic. Now we have parallel computers, so we can easily do similar calculation. So I calculate I do SVM 1000 try. So the smallest number is 68. And here I would like to explain a new method which is called SVM plus. This is a kind of multi-step SVM. In this method, we employ several sets of basis functions, which gives small number of basis functions for SVM. In the present case, as shown in the present figure, smallest number is 68, and the next one is 69. So by using these basis functions, we perform SVM again. But several bases are same as I imagined. Same basis in the 68 calculation and the 69 calculation is 18. So total basis function is 119 instead of 625. I repeat similar same calculation as before, and these are number of basis function employed in 1000 try calculation. Finally, we get convergence result. Smallest number of basis function is 500 for basis function. Finally, I want to compare other machine learning approach. This is a so-called combinational optimization. This is not stochastic variation method. First 20 steps, lowest energy basis functions, which gives the lowest energy, is employed. And from 20, we randomly select 10 basis function and calculate the energy, and most lowest set of 10 basis function is employed, and repeat them about 50 from 50 to 60 basis function. The energy is converging. It's almost same as 54 basis function by using SVM plus. So around 15 basis function is most small basis functions for this three-body system instead of 625 in the original GEM calculations. This is a summary. In the conventional GEM calculation, basis number is 625, and simplest VM 100, and I search the smallest one, it's 68, and multi-step stochastic variation method gives 60, and smallest is 55. And as a reference, I also calculate the other machine learning method, which is called combinational optimization. The result is from 50 to 60. They are comparable to SVM plus calculation. And finally, I want to comment on the reduction of the memory. Basis function reduce one order, so memory memory usage is reduced about 100. I think it's very large value. That's all. Thank you.
Thank you very much. Thank you very much, Aoyama-san. So now session is open for the questions and comments.
Yes.
Do you have any comments or questions?
Yes, someone has question here.
But
Should I go there?
yes, you have to comment on this computer.
No. You can ask here.
Okay,
Yes.
so it's okay, we can
Okay.
discuss. Thank you for this presentation. I'm curious about the machine learning part. So it's basically GPU computation, right?
Not GPU.
Not GPU. So can you elaborate this machine learning? What do you mean by like specific some optimization library are you using, or
No,
what do you mean by machine learning?
I search optimational basis by calculating all combination, almost all combination.
So what's a combinatorial optimization?
Yes, but usually there are several libraries, but in this case, combination is small, so I calculate almost every combination.
Oh, so it's not GPU computation, right?
Not
It's a CPU.
CPU. This calculation is just three-body system.
I see.
Computational time is very quick,
I see.
so we don't have to use GPU. Only CPU is enough.
But interesting, it's important for the application, Helium, right? HE, Helium,
Helium.
application.
Yes, this is helium for atom.
Is it for the nuclear
Nuclear.
reaction?
Bose-Einstein condensation. This is very famous for Bose-Einstein condensation. Usually, we calculate 4 or 5 for this system, but we can expect Bose-Einstein condensation for many alpha atoms.
Okay, thank you. I'm not sure whether they hear me. That's how you
They hear you. It's
Okay.
Thank you for sharing your presentation. I have just one question about the general organization of your paper and work. You have presented very interesting mathematical calculation and quantitative analysis, but my question is about the organization and the structure of your presentation. Could you please clarify and explain what is the main problem associated with your study that you intend to solve in this work? Some kind of explanation about your problem statement.
Yes, what I want to do is reduce the number of basis function And SVM plus is a new method which newly proposed by this presentation. This SVM plus works very well. Usually, basis function is 125, or even using stochastic variational method, it's 100.
Okay.
The present presentation shows the half number.
Okay. Thank you. Is there any other questions?
Matsuhiro-san.
Yes. Okay. Thank you very much. Yeah, Aoyama-san, thank you very much again.
Thank you.
Thank you.
Okay, so we finished 4 talks. So there is one talk not yet presented. So this is the final call. Is there Elise Dudonka or
So
collaborator?
the other presenters are absent, right?
Yes, not yet
Okay,
appeared.
okay. Could you please note that who were absent so that we can note this?
Yep. Okay, the absent speaker is the second talk of this session. So I will note, but
Okay.
yeah. Also,
Second
please remember
presenter.
it. Yep.
Oh, okay. Only second presenter.
Only the second presenter. So other 4 presenter appeared and talked.
Okay, okay. Thank you.
Okay, thank you very much, all the
Thank you. Have a good
talkers
day.
and all the participants. So session closed.
Thank you and have a good day.
Thank you very much.
Please fill the evaluation form. Thank you very much.
Yes, I will feel.
Okay, bye.
Goodbye.